Hello, everyone, and welcome to AISC's live webinar, Design of Strengthening for Existing Steel Members, presented by Joe Schuster of Simpson, Gumpertz, and Hager. Today is March 22nd, 2018. My name is Nate Gonner. I am with AISC's Continuing Education Group, and I will be moderating today's presentation. I want to thank everyone for joining us today. We hope it's a valuable experience. We've got a couple of announcements, and then we'll jump into the presentation. Here's how it works. All participants will be in a listen-only mode for today's presentation. Hopefully you noticed that you have two options for listening to today's presentation. You may listen through your computer streamed over the internet. Alternatively, you can listen through the phone line. You will have this phone option throughout the presentation. Should you experience any technical difficulties with the streamed audio, you can always switch over to the phone. Again, everyone is in listen-only mode. However, as advertised, this live webinar will be interactive. You can submit questions at any time by typing them through the chat feature located on the left of your screen. We will answer questions live at the end of the presentation today as time allows. You can also use the chat feature in case you do have any technical difficulties, such as with the streamed audio. We will respond and do our best to help you with those issues. You might also notice a raise hand feature. Do resist the urge to use this feature. The better way to communicate with us is using the chat feature. We see all the questions that you type into that chat. For legal reasons, I must announce that today's presentation is being recorded. AISC is a registered provider with AIA, the American Institute of Architects, and today's presentation is registered with AIA for continuing professional education. In conjunction with that registration, we need to inform you of the description of today's presentation, as well as its learning objectives. We had this information on the screen leading up to the presentation, so hopefully you've had a chance to view that information. We do intend to fulfill these learning objectives. A couple of announcements regarding PDHs. For those of you seeking PDH credit, everyone that is at your connection today is eligible to receive a certificate for attending. Within 2 business days of today's session, you will receive an email with information on how to report your attendance and ultimately claim your PDHs. You will receive this email from the address registration@aisc.org. That email will contain a link to an online form. And using that online form and your AISC website username and password, you will be able to fill out that form and receive PDH certificates via email. Again, that email will be coming from registration@aisc.org. I will touch again on this in our closing announcements today. But as for now, that is my final announcement. I would like to introduce today's speaker, Joe Schuster. Joe is a structural engineer working in the New York City office for the engineering firm Simpson, Gumpertz, and Hager, a national engineering firm that designs, investigates, and rehabilitates structures and building enclosures. Joe's focus is on the repair and adaptive reuse of historic steel structures in the New York metropolitan area. He is the co-author of the newly updated Design Guide 15, the AISC Rehabilitation and Retrofit Guide, which will be available for purchase soon. Joe, thank you for being here. I'll now turn the floor over to you.
All right, thanks, Nate. So as Nate mentioned, there is a new version of Design Guide 15, the second edition that will be coming out, I believe, in the next month or so. and a lot of the information that I will be covering is available in that design guide. So before I begin, just a brief outline of what I'll be talking about. I'll go over some typical situations where you may need to evaluate or strengthen an existing steel member. Then I'll talk about some code requirements, including some applicable sections of the IEBC, the International Existing Building Code. I'll talk about the Appendix 5 and the AISC specification. Then I'll talk about how to go about evaluating an existing steel member, including how to determine material properties and dimensional information of historic steel members. And then I'll go over several strengthening examples and discuss different ways to strengthen beams, columns, and connections. So why you might need to strengthen an existing steel member. One case that happens quite often is that you're changing the loading to that member. So for example, if you had an existing building that's being expanded, adding a story above the existing roof, then the roof beams and potentially the columns of the existing building would need to be evaluated and strengthened. Another situation that happens quite a bit is a building if it has a change of occupancy. For example, a building that was originally designed as an office building with a live load of 50 pounds per square foot, if it's being changed to an assembly area with 100 pounds per square foot, then the steel framing may need to be strengthened to accommodate that additional load. Another condition may be is if you're changing the dead loads in the existing structure. For example, if you're replacing light finishes with heavier finishes such as concrete, if you're building up the floor elevation, or one situation we come across often here in New York is tenants need to install these high-density file systems shown on the right here. These can weigh quite a bit and often require strengthening for the existing floor framing below. Another situation may be reframing. So often we'll need to put in new stairs, new elevators within an existing building. In order to accommodate these, we may need to cut and reframe the existing framing, which can change the load to existing members. As an example, this framing bay here on the left, the existing beams originally went all the way across this bay. And then in order to accommodate this stair opening, we had to frame off these beams with a new beam here, which added load to this existing beam, which then needed to be strengthened. Another category of why you may need to strengthen or evaluate an existing member is for repairs. As an example, if you have fire damage or impact damage, such as this column, it may need to be evaluated, and then repairs may need to be designed, such as heat straightening in the case of this column. Another common occurrence would be corrosion, which often results in section loss to the existing steel. A bad example of that is shown here in this photo. And in this case, obviously, the structural engineer would need to get involved in evaluating that beam and designing strengthening. And then a whole other category of strengthening would be seismic retrofit. I'm not going to have time to cover that topic here today, but many of the theories and the design provisions that I'll go over can be used and applied to a seismic retrofit as well. And I've listed here two references that cover that material, ASCE 41 and FEMA 547. So I'll talk just briefly about the International Existing Building Code, which is a code that is governing in a lot of places in the United States, and a few sections that pertain specifically to strengthening of existing gravity members. So the IEBC defines three different types of work, classifies work into three categories: repairs, additions, and then alterations, which are subdivided into three different work classes depending on the scope of work. For repairs, it says that for repairs less than substantial structural damage, the damaged elements shall be permitted to be restored to their pre-damaged condition. So substantial structural damage is defined as members vertical elements of a lateral system that are reduced by more than 33%, or vertical gravity members that support 30% of the building and are reduced by more than 20%. So even though something like this may look like substantial structural damage only, really vertical load-carrying members such as columns that are substantially damaged would fall under that category of substantial structural damage. And the IEBC therefore would allow you to just restore the original size of this member when performing repairs. Now, it's always a good idea to understand why the member failed in the first place, and make sure that your repair is addressing the cause of the original failure where appropriate. So for example, if this beam is getting wet, causing the corrosion, you would want to make sure that your repair design prevents that from happening again. So another category of work in the IEBC is additions, which is defined as an increase in floor area, number of stories, or height of a building or structure. And what the code says is that the existing structural elements supporting any additional gravity load as a result of additions shall comply with the International Building Code. But there's one exception, that structural elements whose stress are not increased by more than 5% don't have to meet this requirement. So when you're looking at a member that is affected by your addition, if the load to that member is increasing by less than 5%, then you wouldn't have to do anything. But if it's more than 5%, then the existing member would need to be designed to the International Building Code. So that means using the current loading requirements and strength provisions of the IBC. And then the third category of work is alterations, which is basically anything that's not a repair or an addition. And basically the same provision applies, that any element where the loads are increasing by more than 5% needs to be designed to the International Building Code. And there's also an additional provision that alterations cannot reduce the capacity of the load-carrying structural element unless it is demonstrated that the elements have the capacity to carry the applicable design load. In terms of code provisions that are applicable specifically to steel, you'll want to be familiar with Appendix 5 in the AISD specification. It's in the back of the spec. It's about 5 or 6 pages long. That contains some specific guidelines on how to evaluate existing steel members. And basically it gives you two options for doing that analysis. You can do it either by structural analysis or by load test, or a combination of the two. So looking at the language in Appendix 5, I put together this flowchart that basically describes the procedure for evaluating and then designing strengthening for existing members. So the first step is to calculate the load effects on the members, and you do that using the current loads in the, either from ASCE 7 or whatever the applicable building code is. If IBC is the applicable code where you live, then if the change in load is less than 5%, then you wouldn't need to strengthen that member or even evaluate it. If the change in load is greater than 5%, then you have two options for doing your analysis. Either evaluation by analysis per section 5.3 or evaluation by load test by section 5.4. So if you're doing the evaluation by analysis, you're going to need to determine the material properties and the dimensional information, specifically the cross-sectional properties of your historic steel shape, and then you'll determine the available strength using the current AISD specification. So if the historic member is adequate for this analysis, then you don't need to strengthen. If it's not adequate, then you'll need to design strengthening, and we'll talk about some ways to do that. Now, the other option you can do is load testing. Now, this is typically or very rarely done because evaluation by analysis is typically much cheaper. Usually it's easier to do a field survey, review the drawings, and determine the strength that way rather than loading the structure and installing instrumentation in order to perform a load test. But in some situations, for example, if you think there may be some additional strength in the structure that you can't account for through analysis, you may want to do a load test. So in Appendix 5, it gives the procedure for doing that. You'll want to install temporary shoring in case there is a failure. And then once that's installed, you load the structure to the factored gravity load, typically 1.2 dead load plus 1.6 live load. Hold that load for an hour, And the code says that in order to pass the test, the deformation after the hour has gone needs to be less than 10% of the deformation at the beginning of the holding period. And then there's also some language that talks about evaluating the permanent deformations, but there's no specific criteria that needs to be met there. So again, if you meet the load test, then you don't need to design strengthening. If you do not pass the load test, then strengthening will be required. So looking specifically at the language in Appendix 5, it says the load effects shall be determined for the loads and factored load combinations in Section B2, and then the available strength of members and connections is determined from the applicable provisions of Chapters B through K of this specification. So again, when you're looking at historic members, you want to use the current loads and the current strength provisions, as opposed to, say, you have a structure from the 1960s trying to look up the specification that was applicable at the time of original design and evaluate using that instead. So in order to do your evaluation by analysis, you'll need to know something about the material properties of the existing steel, which may be different than steels that are commonly specified today. So Appendix 5 says the engineer of record is responsible for determining the specific tests that are required from sections 5.2.2 through 5.2.6. So that includes material property testing to determine tensile properties, to determine chemical composition in order to determine whether or not the existing steel is weldable, notch toughness, which is typically only required for tension splices of heavy shapes, strengths of weld metals, and strengths of bolts and rivets. So it's the engineer record's responsibility to determine what tests are required and how many samples you need to take. Before you proceed with any testing procedure, it's always a good idea to do whatever you can to try and find the original drawings, because they're going to save you a lot of effort if they can be found. So check in a lot of places to try and find those drawings. If they're not readily available with the building owner, you may want to check with the local building department or local libraries or state archives. So in order to do your evaluation, you'll need to know the tensile properties of the steel, typically F sub U, the tensile strength, and F sub Y, the yield strength. So the engineer of record is required to determine the number of tests that you need to do. If you have reliable project records that can give you reliable information about what steel was used in the original construction, then you don't need to test. You can just rely on that information in your analysis. If reliable records are not available, then you'll need to take steel coupons from the existing building and pull test them in accordance with ASTM A370. So typically those samples are taken from an area of low stress in a member. So typically that would be from the flanges near the ends of an existing beam. And when you're taking these samples, you're typically not looking to get a statistical sample, a large number of samples, and then calculate a minimum F sub Y. You're taking just a few samples and then trying to match your results to a material, a historic specification that are available in Design Guide 15, and then use the minimum FY and FU of those specifications. So when you're trying to determine the tensile properties of the steel, just knowing the year of the original construction can be very helpful, and knowing something about the history of different types of steel. So the first structural steel specifications for A7 steel for bridges, A9 steel for buildings came out in 1901. Those steels had minimum tensile strength of 55 KSI and a minimum yield stress of half of the tensile strength. In 1939, the A7 and A9 specifications were merged. And then in the early 60s, A36 steel was introduced and became more prevalent. And then beginning in the 1970s, grade 50 steels became more common. So other than the tensile strength, the other thing you're going to want to know about your existing steel is whether or not it's weldable. As we'll see from the strengthening examples, you'll often need to weld to the existing steel in order to strengthen the members. So the first thing to do when you're working in an existing building is to look around and see if any of the existing connections utilize welding. If they do, that's a pretty reliable indication that the existing steel is weldable. Most steel buildings built after about 1963, when A36 became more prevalent, are generally weldable, but steels before that, it depends. So you'll need, in that case, if you don't know whether or not the steel is weldable, you'll need to do what's called a chemical composition test. In order to do this test, you'll take a small sample of the steel. It can be just a few shavings, is all you need. Send it to a lab, and they'll send back a report that looks something like this, that gives the different components, different elements, and their percentage of the composition of the steel. And then they'll typically calculate for you what's called a carbon equivalent value using this equation or a similar equation. So steels with a carbon equivalent value of less than about 0.45 are generally considered weldable and can be welded using the same procedures as you would for a new piece of steel. So as I mentioned, most steels after 1963 are generally weldable. Before that, you need to evaluate it on a case-by-case basis. So historic steels that were in production before that, the ASTM specification covered the minimum strength, but they didn't provide limits for things like the carbon content, phosphorus, sulfur, and these are things that can cause problems with welding. If you have too much carbon, it can cause high hardenability and low ductility. If there's too much phosphorus, it can create increased brittleness in the steel and weld cracking. If there's too much sulfur, it can result in porous welds. So if you have a carbon equivalent value of about 0.45 or less, then it can be welded using standard procedures. With a carbon equivalent value higher than that, in the range of 0.45 to 0.6, it may be possible to weld to it, but you'll need to preheat the steel. So preheating the steel will slow the rate of cooling and reduce the risk of cracking. If the carbon equivalent is larger than 0.6, it's going to be very difficult to weld to that steel, and you probably will want to consider using a bolted reinforcing detail instead of welding. For more information about how to weld to historic steels, I recommend reading up on this resource below. It gives detailed information about how to do that, including steels with high carbon contents. One way to test your welds, if you're unsure about the quality, is to do what's called a tab plate test. So to do that, you take a 1/4 inch by 2 inch by 2 inch plate and install a 5/16 inch fillet weld on one side, and then hit it with a mallet. If the steel bends and if the weld fractures through the weld, that's an indication of a good weld. If the weld fractures at the interface between the weld metal and the existing steel, that's a sign that your steel is probably not weldable and it's not a good weld. Something else to consider when welding to existing steel is that when you're welding to a loaded member, the steel is going to lose strength when it heats up, because the welding is going to create temperatures in excess of about 650 degrees where steel begins to lose strength. So I'll talk about this in more detail when I talk about strengthening loaded columns, but something that really needs to be thought about carefully in that case. In general, as a result, you'll want to design welds that limit the heat input into the steel. So to do this, in general, you'll want to design your reinforcement to use fillet welds instead of groove welds. Use the smallest weld size that's adequate for the loads. As engineers, often we'll just bump up the sizes of members and connections in order to provide additional factor of safety, but that may have detrimental effects if you're welding to a loaded steel member. You'll want to use intermittent welds wherever possible to limit the total amount of welding. You'll want to try and avoid overhead welding because this will result in a slower deposit rate. It's not always possible to avoid it, but you should avoid it when you can. The slower deposit rate will cause the steel to heat up over a greater area. And you want to avoid welding across stress lines. So in addition to the existing steel beam and column properties, if you're evaluating an existing connection, you'll also need to know something about the properties of the existing steel bolts and rivets. So Section 5.2.6 in Appendix 5 covers this. It says that you're allowed to look for markings on existing bolts. If they have markings, you can use that in order to determine the strength. In the absence of information, the Appendix 5 allows you to make some conservative assumptions about the materials for bolts and rivets. So for bolts, you can conservatively assume A307, and for rivets, ASTM A502 grade 1. So typically it's easier to make these conservative assumptions rather than trying to remove bolts and rivets and test them in a lab. But if you needed to do that, you would test in accordance with ASTM F606. So after you have your material properties, the other piece of information that you're going to need in order to do your evaluation is dimensional information. So this includes things like spans, column heights, bracing locations, and most critically the cross-sectional properties of historic members. So again, it's very important to try and look for existing drawings because they're going to help you a lot if you can find them. Typically, historic drawings will look very similar to what we would produce today. Some of the notation for beams might be a little bit different, but the information is pretty consistent. So for example, this beam here is listed as 8B17. That indicates a beam that is 8 inches or approximately 8 inches deep and weighs 17 pounds per linear foot. And if you go to the tables in Design Guide 15, you can find the cross-sectional properties for that. If you don't have drawings, then you're going to need to do probes in order to determine the dimensional information that you need. And it's also a good idea, even if you have drawings, to do to take a few dimensions in the field in order to confirm the accuracy of the drawings that you have. So to determine a beam or column size, typically you'll need to just measure the beam depth, the beam flange width, and the flange thickness. And then you can take that information and find a section in Design Guide 15 in the tables there, and then get the cross-sectional properties that you need for your analysis. When you're out in the field doing your field survey for the existing members, it's also a good idea to measure slab thickness and get other information that you need in order to accurately determine dead loads and other similar things. So as an example, if you're measuring a beam out in the field, your field notes might look something like this. You'll get the flange width, the flange depth, and the flange thickness. Flange thickness, you'll want to take a couple measurements, one kind of at the tip of the flange and then another one closer to the fillet. As historic shapes, a lot of them have sloped flanges, and the historic tables will give you an average flange thickness. So this is a printout from a table in Design Guide 15. So you take the dimensional information that you got from the field, match it up with the shape in the table, and then from that same line you can get the cross-sectional properties that you need in order to do your analysis. You also want to cross-reference or take a look at this source reference number, which is in these tables listed here in Design Guide 15, and make sure that the beam that you've found that you think matches with what you measured in the field matches up in terms of the year that your building was built and the year that that historic shape database is from. So you also need to know some dimensional information about connections if you're evaluating connections. Usually it's pretty easy to measure both diameters, but for rivets it can be difficult to get the diameter of the shank because you can usually only get access to the rivet head diameter. This table from Kidder and Parker, which is a great reference for historic construction, and includes a lot of details about historic slab construction and riveted connection, provides these tables that gives you the relationship between the diameter of a rivet head and the shank. So for example, if you measure in the field a rivet head diameter of 1 1/4 inches, that would correspond to a shank diameter of 3/4 of an inch. So again, the general design procedure, this time just looking at the evaluation by analysis and not the load testing. So you'll calculate the load effects using the current code, determine the material properties through a combination of reviewing project documents and doing testing. You can determine the dimensional information that you need from the tables in Design Guide 15, and then you evaluate the strength using the current AISD specification. If the strength is okay, then you don't need to strengthen. If it's inadequate, then you'll have to proceed with designing strengthening. So let's do a quick example looking at strengthening of an existing beam. So in this example, we have an existing beam, a W12 by 16.5. It's spanning 20 feet and has a load on it of a factored load. We'll be using LRFD of 1.29 kips per foot. The building was built in 1965, and we know from the project documents that they used A36 steel. So we're going to assume that the beam is fully braced for lateral torsional buckling, braced by the slab, and we're going to evaluate the beam and design strengthening as required using a welded plate at the bottom flange. So from the load, we can calculate WL squared over 8, the flexural demand of 64.5 kip feet. So from Appendix 5, we're going to evaluate the beam using the equations of the current specifications, not trying to use the allowable stress provisions from a historic specification. So the idea here is that we want to use the latest and greatest in terms of determining strengths of members and take advantage of all that we've learned from research about steel strengths when we're evaluating historic members. So for this particular problem, the nominal strength is just equal to the plastic moment, since lateral torsional buckling is not applicable. So F sub y times the plastic section modulus. So we know our moment demand, we know F sub y, so we can solve directly for the plastic section modulus that we need, and we get a value of 23.9 inches cubed. And then if we take a look in Design Guide 15 for this historic shape, we can get the geometric properties, the relevant geometric properties for this shape. And taking a look at that table, we see that the existing beam has a plastic section modulus of 20.6 inches to the third. So that's less than the required plastic section modulus, so we're going to need to reinforce this beam. So the existing beam is overstressed by approximately 16%, so we'll need to design reinforcing that increases the plastic section modulus from 20.6 inches cubed to 23.9 inches cubed. Now before proceeding with strengthening, it's always a good idea to try and sharpen your pencils and make sure that you're not being overly conservative with any of your loading or your analysis. So a couple things to think about. You want to make sure that you're not being overly conservative with your dead loads. Go out to the building and try and determine exactly what the slab thicknesses and finishes are, what the ceiling weights are, mechanical equipment weights are, so that you're not overestimating that. Since we're using the current provisions for loading, we're allowed to use live load reduction. Even though it may not have been applicable during the original design, you're allowed to use it now. In this particular example, it's probably not going to be of much benefit for a beam, but if you're looking at a girder or especially a column, that's something you'll definitely want to consider. You want to check and make sure that your spans are not overly conservative. If you have a girder spanning from the flange of a column to the flange of a column, you can use the clear span instead of the center to center span. If you use LRFD instead of AISD for gravity members, typically that will get you an extra couple percent of capacity, so consider doing that if that'll make the difference between having to reinforce and not having to reinforce an existing member. And then lastly, you should consider testing if you're relying on some conservative assumptions about the material properties. So some common welded reinforcement configurations. In most situations in buildings, you'll have a slab above the top flange, so you'll really only have good access to the bottom flange. So one typical way of reinforcing is just by adding different steel shapes to the bottom flange of the member. So typically you'll want to design those to be wider than the existing bottom flange so that you can use topside welding instead of overhead welding. And by adding the reinforcing, what you'll be doing is basically shifting the plastic neutral axis down. In order to evaluate the flexural strength of the member, you'll have to find the plastic neutral axis, which is located where Fy times the area above the plastic neutral axis is equal to the Fy times the area below, and then the nominal moment strength, flexural strength, is equal to the summation of the Fy times A times D, where D is the distance of one of the parts of the beam broken down into rectangles from the plastic neutral axis. Some other common configurations for welded reinforcing. To get a more symmetric reinforcing, where possible, you may want to put a plate on the bottom and the top. If you have a slab on top, you could look at welding plates to the underside of the flange. For cases where torsional loads or lateral torsional buckling are applicable, you'll want to look at creating closed shapes with your reinforcing. So this can be done by adding plates between the flanges or angles to either the bottom flange or the top flange or both. And then a very common reinforcement technique is to add a WT shape to the bottom flange. This will add quite a bit of area away from the neutral axis, which can be effective in drastically increasing the flexural strength of the member. One thing you'll want to look out for some heavy WT shapes, you want to make sure that the flange of the WT is not so wide that you won't be able to weld. And I guess the downside of the WT configuration is that you have to use overhead welding. But sometimes it's necessary for beams that need to be strengthened quite a bit. So to do our analysis, we'll be using the provisions of the current specification. And I'll discuss here briefly the problem with using an allowable stress approach from an old code. So when I say allowable stress, I'm talking about using the provisions of a historic specification where steel was typically designed by looking at the elastic stresses in the beam and then limiting them to a value typically either 0.6 or 0.66 times Fy. So if we were trying to reinforce this beam using this approach, we would need to keep the elastic stress below 0.66 times the yield stress, or 23.8 KSI. In order to do that, we would need to consider the history of the loading. So you have a stress in the beam initially before the reinforcement is installed from the dead loads that are present before the reinforcing is installed. Then after the reinforcement is welded into place, you have additional stresses from the superimposed dead loads and the live loads, and then you add those two together to get this stress diagram of elastic stresses in your reinforced section. So as you can see, this design is effective in limiting the stresses below the allowable, but it's a very conservative design because it doesn't take advantage of the strength-based approach of the current AISD specification. And we'll see in this example that we can use a much smaller plate instead of this large tube to achieve the same strength. So if we're going to use this approach, we're going to ignore the current specification. We're going to ignore the loading history, except for some serviceability checks. And then we're going to rely on redistribution of the stresses and using the plastic strength of the reinforced section. So in this example, we'll use the strength-based approach from the 2016 AISD specification in order to size the reinforcement. So the sizing of reinforcement is an iterative process. It's best to set up a spreadsheet that calculates the strengths for different reinforcing configurations so that you don't have to do a bunch of iterations. But I'll show here just the final iteration where we'll use a 5-inch wide plate that's a 1/4 inch thick at the bottom flange. So the 5-inch wide plate was chosen because the flange width of the existing beam is 4 inches wide. So we want a plate that's wider than that so we can weld from the top side and not have to do any overhead welding. So in order to evaluate this reinforced section, we're going to break the section down into different rectangles, a rectangle for the top flange, a rectangle for the fillet area, rectangles for the web, and then we'll locate the plastic neutral axis. So in this case, because the existing beam and the reinforcing plate are both A36 steel, the plastic neutral axis is just equal to where the area of steel above the line and below the line are equal. So from your spreadsheet that you set up, you can find that the plastic neutral axis is equal at 8.72 inches from the top flange. So this calculation here sums up the areas above that line and below the line and shows that they're equal. So that's a check that you've correctly found the plastic neutral axis. And then once you've found that, you can find the plastic section modulus by just summing up the areas of those different rectangles times d, which is the distance between the centroid of that rectangle and the plastic neutral axis. So if we do that, we find that this reinforced section has a plastic section modulus of 26.6 inches cubed, which is greater than the 23.9 that we needed. So now that we've sized the reinforcement, we need to design the welds between the plate and the existing beam. Now the reinforcing is not required over the full length of the beam. You could put it over the full length, but really you only need the plate over the section of the beam where the moment demand exceeds the capacity of the unreinforced section. So this, looking at the moment diagram, we can calculate the strength of the existing beam at the theoretical cutoff point. That's what these dashed lines represent. So the flexural capacity of the unreinforced section is equal to 55.6 kip feet, and then looking at the moment diagram, we can see that only the portion of the beam, the 7.5 foot long portion of the beam in the middle, is the only portion of the beam where the required flexural strength exceeds the capacity. So that's the area where you need reinforcing, but then we'll need to extend or develop the reinforcement on either side, similar to how you would do with the design of reinforced concrete. And then section F13.3 has some prescriptive requirements for cover plates, and it says in the code, the reinforcement must extend beyond the theoretical cutoff point and must be attached with flip critical bolts or fillet welds. So in order to design the termination welds at the ends of our reinforcing plate, we're going to use the yield strength of the plate, and that comes from the commentary from section F13.3. So the yield strength of the plate is just equal to the yield stress times the area, so we get a value of 45 kips. And then we can solve directly for the length of a 3/16 inch fillet weld that we need in order to develop that force. So our force is 45 kips. We have welds on both sides of the plate, 2 welds, and the strength of a 3/16 inch fillet weld is 4.18 kips per inch. So we can solve directly for the length of the weld as 5.38 inches, and we'll round that up to 6 inches. There's also one prescriptive requirement in section F13.3 for cover plates, and it says that the cover plate, the termination, needs to be at least a length of A prime. If you provide a continuous weld equal to or larger than 3/4 of the plate thickness across the end of the plate, then the length of the termination weld needs to be at least as wide as the reinforcing plate. So in our case, we have a 5-inch wide plate. If we provide a weld at the end of the plate, then the 6 inches weld that we just designed is adequate. If we didn't provide a weld across the end of the plate, then the termination welds would need to be a length of 2W or 10 inches. So in order to minimize the total amount of required welding, we'll add that weld across the end of the plate to meet this requirement. And then the last thing we need to do is design the welds between the theoretical cutoff points. So those welds are going to be designed for the shear flow. Conservatively, we'll take a look at the shear flow at the theoretical cutoff point. So if you look at the shear diagram, you can find the required shear strength at that point, and then calculate the shear flow as VQ over I, where Q is equal to the area of the plate, the reinforcing plate, times its distance from the centroid of the reinforced section, and then I is the moment of inertia of the reinforced section. So in these equations, the value y bar is equal to the distance from the top of the reinforced section to the centroid. The centroid is not the same thing as the plastic neutral axis. So from this equation, we find that we have a shear flow of 0.208 kips per inch. So we need to design our intermittent welds between the terminations for that force. From specification section J2.2b, part E, it gives us some minimum requirements for weld sizes of 1.5 inches long. So we'll consider 1.5 inch long intermittent welds at 12 inches on center, both sides staggered. We calculate the strength of that weld. We get a value of 1.05 kips per inch, which is quite a bit greater than the required strength. So here's our final design. We have our existing beam. We have our 1/4 inch reinforcing plate, which extends over the 7.5 foot length between the theoretical cutoff points, plus an additional 6 inches on either side for the development welds. We have our 6-inch long 3/16 inch welds, plus an additional weld across the end of the plate, and our intermittent welds between the ends. So some other checks that you'll want to do when looking at a beam, you should check the shear in the unreinforced beam. Typically that doesn't control, but again you would do that using the equations in the current specification. You'll need to evaluate the existing connection if you're increasing the load to it by more than 5%. I'll go through an example of how to do that and how to design strengthening if needed. You'll want to check the entire load path of your system. If you're increasing the loads throughout the whole slab, you'll need to also make sure that your slabs are adequate, the girders are adequate, the columns, if you're increasing your load to them substantially, may need to be evaluated as well. And then lastly, you'll want to take a look at deflection. So for deflection, unlike the strength where we ignored the loading history, for deflection you'll need to consider the loading history. So you'll have some deflection component that occurs before the reinforcing is installed, and then an additional deflection component that occurs from the superimposed dead loads and live loads that are applied after the reinforcing is installed. And in order to determine those deflections, you'll want to create a simple computer model with a step section that has the unreinforced moment of inertia along the ends, and then the reinforced moment of inertia along the reinforced portion of the beam. So typically if your deflection criteria is meant to limit damages to finishes, if that's the case, then you're probably only interested in considering the deflections that occur after the reinforcing is installed. Another thing you'll want to check related to serviceability is to check the elastic stresses in the beam. Is a good idea, especially for heavily reinforced sections. Although we didn't have to consider the loading history for the strength check, it's a good idea to see in the reinforced condition, considering the loading history, whether or not the stresses at the top of your beam are approaching yielding. And if they are, you'll need to consider some additional permanent deformation may be occurring. And if that's not acceptable, you may need to increase the size of the reinforcing. So how this is done is, first, again, you'll take a look at the stresses in the beam before the reinforcement is installed. Then you'll calculate the stresses of the reinforced section for the superimposed loads. Add those two together to get your overall stress diagram. So in this particular case, our stress at the top is 27.7 KSI. This is under service loads, by the way, not factored loads. So in that case, in this particular case, we're still not getting very close to the yield stress of 36 KSI, so we don't need to worry about permanent deformations. If you did have a case where the top of the beam, the stresses at the top of the beam were approaching yielding or exceeding them, you may want to think about trying to jack some of the load out of the existing beam before installing the reinforcing. So how this is done is the reinforcement is laid up but not welded to the beam. Then you would jack some load out of the existing beam, and then once that's done, then you can weld the beam or weld the reinforcing to the existing beam. So that will help to reduce the overall deflections and also the elastic stresses at the top of the beam. So that's it for our example. I'll talk about some other situations that you may come across. So the beam we looked at in our example was a non-composite beam. If you had a beam that was composite with a slab with shear studs, the approach for designing strengthening would essentially be the same, except you'd have an additional internal force from in the concrete and compression. So again, the approach is basically the same. You're going to break your section down into equivalent rectangular sections. Find the plastic neutral axis. In this case, the plastic neutral axis is going to be located where this internal forces above the line is equal to the internal forces below the line, the plastic neutral axis line. And then once you have those internal forces calculated, then you can find the flexural strength, which is equal to the sum of these forces times their distance from the plastic neutral axis. In cases where lateral torsional buckling is a consideration, you'll need to use the equations of specification section F4.2 for singly symmetric shapes if you're using a single plate reinforcing detail. It can be a little bit cumbersome, but it's definitely doable. If you're looking at a beam where you have lateral torsional buckling or applied torsional loads, and you're only reinforcing across a portion of the member, you'll want to take a look at this paper as the equations for that become even more complicated. And also, if you have a beam where torsion is a consideration, you'll want to consider using one of these reinforcing configurations where you're creating a closed section that's more resistant to torsional loads. So some other strengthening schemes that you can consider. If you have a beam framed with these W12s, instead of trying to reinforce those members, you could look at adding new beams between the existing beams. So if you do this, your design will have to consider the loading history, because the new beams are only going to be able to resist loads that are applied after they're installed. And then you also want to consider the effects on the existing slab. So in one sense, you're benefiting the slab by reducing the span by half in this case. but you may be introducing negative moments above your beam, which could cause cracking in the slab. So something that you'll definitely want to think about. And then you'll also need to consider how these beams get installed. In order to avoid the flanges of the girders, they may need to be spliced in the air or have long connection plates at the ends. So that reinforcing scheme would address the beams but not the girders. One way to reinforce girders, if you don't want to weld reinforcement to the bottom of them, if you want to limit the amount of field welding, is you can just install a new member directly below that existing member and then shim it directly to the underside but not weld to it. So in this case, again, it will reduce the amount of field welding, but you'll need to consider the loading sequence, as the reinforcing beam is only going to take loads that are applied after it's installed, obviously, but also it'll only take loads in proportion to its relative stiffness to the existing beam. So this reinforcing scheme, while it reduces the amount of field welding, you'll still need connections at the end to connect to the columns, and it's limited in where it can be used because of the headroom restrictions that it imposes. But it may be you may be able to use it in some cases in spandrel conditions or similar. Another option for reinforcing existing framing is to introduce new columns to basically reduce the span of the beam. So if you introduce new columns, you'd probably also need to introduce new footings. In this particular case, you could also look at using diagonal posts, which wouldn't need a new footing. But again, you would need to consider, so these posts would essentially help to limit the span of the existing member. You'll need to again consider the loading sequence, as the posts are only going to be taking loads applied after the beam is installed. And in this particular configuration, you may get negative bending moments towards the ends of the beams. So you'll need, if you're relying on the slab to brace your beam, you may need to install additional bracing to brace the bottom flange. In addition, you'll need to consider the entire load path of a reinforcing scheme such as this. So if you put in these diagonal posts, you're going to get a small amount of compression in the existing beam, which is usually not an issue, but you're also going to get a small amount of tension in this beam below, so you'll need to make sure that that beam, and especially its connections on either side, are able to deliver those loads to the beam. Another strengthening technique that is pretty elegant when it can be done is to add shear studs. So if you have an existing beam, a concrete slab, and the beam is not composite or it's not fully composite with the existing slab, then you can add new shear studs that introduce composite action. So this is done by creating discrete cores through the existing slab. You have to be very careful not to damage the top flange of the existing beam. Also, you'll need to be very careful about controlling the water that's used during coring. Make sure that that is not going to damage the space below. But if you can do this, then it's usually a good solution, because you don't need to have access to the underside. The strengthening can be done from the top side. You'll need to also think about if there's reinforcing in the slab, what the coring is going to do in terms of the slab strength. And then once the studs are installed and inspected, you would come back and fill them with non-shrink grout in order to restore the continuity with the existing slab. So one last strengthening option is post-tensioning. Again, this is a good option for conditions where headroom may be a restraining condition, where you're not able to add to the depth of the beam because this particular scheme can be done within the depth of the existing member. So in this case, what you're doing is adding tension rods near the bottom flange of the beam, and those get tightened in order to create a compression force along the bottom that counteracts the positive moment that's in the beam. So this paper here, discussion and strengthening of existing composite beams using LFD procedure, is a good one to read if you're interested in learning how to evaluate and design this kind of strengthening. So in most of the strengthening schemes that I've discussed so far, except for the shear stud, you're going to need access to the bottom side of the existing beam. In some cases, that may not be possible. Your floor is the floor above the beam. In a lot of cases, you may not be able to access the beams below because there's a different tenant, or perhaps it's the lobby. So you may need to try and reinforce from the top side. So this is an example of where we reinforced existing beams from the top side in New York, where we're on the second floor and we weren't able to access the beams below. So in order to accomplish this, we had to cut through the slab from the top side very carefully to expose the top flange, and then as the demolition contractor worked, as soon as they removed a small portion, they welded the deck back to the existing beam. And then we installed reinforcing, system of reinforcing plates and angles, and a new slab that basically raised the existing slab. So it's a lot of work, but sometimes you may need to use a procedure like this if you don't have access to the underside of the beam. So that's it for beam strengthening. I'll talk now about column strengthening. Again, the same design approach that we use for beams will be used for columns. I'll calculate the load effects using the current code, determine material properties and dimensional information from Design Guide 15 or through testing, and then we'll determine the available strength using the current code, and then, if needed, design strengthening. So typically, columns are reinforced similar to beams by using welded plates. Wherever possible, you're going to want to use a symmetric reinforcing configuration so that your column section remains doubly symmetric. By adding steel plates, you're going to be adding to the cross-sectional area and the moment of inertia, so that'll give you the additional strength that you need. So you want to use a symmetrical configuration wherever possible. In some cases, it may not be possible to use a symmetrical configuration. For example, if you have a column that's embedded in a wall and you only have access to one flange, you could try a reinforcing scheme like this, but you'll need to be very careful about doing that because if you're welding on only one side, you have the potential to create welding distortions that are going to introduce P delta effects into your column. So when we were looking at reinforcing beams, this wasn't much of an issue because welding to the bottom side is only going to help in terms of the overall deflections, but for columns it can really create some problems. So if you're going to be using a single-sided asymmetric reinforcing configuration, you're going to want to quantify what this distortion is and make sure you've accounted for it in your analysis. So I recommend referring to this reference here, Design of Welded Structures, which has some equations for quantifying this welding deformation. And even for symmetrically reinforced columns, this is something you'll want to think about because if the reinforcing is not installed at the same time, you could have this, the two welded plates are not installed at the same time, you could have this deformation temporarily. Another thing to consider, which I mentioned previously, but it's particularly relevant when looking at columns, is that the temperature is going to exceed 650 degrees, and at that temperature the steel will begin to lose strength. So taking a look at this chart, you can see that this is the temperature of the steel at a distance away from a 1/4 inch weld along the length of a member. So you can see that portions of steel within about 1 inch to 1.5 inches away are going to exceed that temperature and begin to lose strength. And then this is a relationship of the distance from that weld to the strength. So you can see that at about 1 inch away, you have about 60% of the steel strength, and then as you get closer to areas within a ½ inch of the weld, you have almost no strength. So how this is typically dealt with in design if you're welding to a loaded column, as you consider the area within an inch or two of the weld to be ineffective or is inactive, basically no strength in that area, and then evaluate the remaining section and make sure that that is still adequate for the loads, not the final loads, but the loads that are present at the time of welding. And again, you'll want to follow these general guidelines in order to try and limit the heat input to the existing steel. And then one last thing to consider when looking at columns is the preload, which is the load in the column at the time of strengthening. So when we looked at beams, we ignored the loading history. And it turns out for columns that you can do the same thing where you ignore the load that's in the column at the time of strengthening, provided that the reinforcing is stabilizing. And what's meant by that is that the least radius of gyration of the reinforced column needs to be equal to or greater than 85% of the radius of gyration of the unreinforced column. So this finding was found through physical tests of reinforced columns and finite element models. If you want to read up more about it, you can take a look at these references that are listed in detail at the end of the presentation. So if you have a case, in most cases, if you're reinforcing the column, this criteria is going to be met. But in rare cases where it's not, you would need to consider the loading history, where the reinforcing plates are only going to take the load applied after the reinforcing plates are installed. So let's take a quick look at an example here. We have a column where the loads are increasing. The final applied load is 550 kips, factored load for LRFD. The existing column is A7 steel with a yield strength of 33 KSI. The column size is a 10 WF66. And we're going to evaluate this column for the applied load and then design strengthening. So we're not able to take a look in the manual table 4.1 to quickly determine the strength of this column because the historic shape is not listed there, and also the yield strength 33 KSI is not covered in the table. So we'll need to get the geometric properties from Design Guide 15. In particular, we'll need the area and the least radius of gyration about the y-axis, and then we can use the equations and specification Chapter E, Part 3 in order to determine the strength. So the effective length for a pin-pin condition is just the 1.0 times the length of 16 feet or 192 inches. Then from equation E3-4 we can find the elastic buckling stress, which is equal to pi squared times E divided by the slenderness ratio squared, so we get a value of 51.6 KSI. And then we'd calculate the critical stress. Since Fy over E is less than 2.25, we use this equation from the specification and get a critical stress of 25.2 KSI. The nominal compressive strength is then equal just to the critical stress times the area of the unreinforced column, and we get a value of 489 kips. And then we multiply by the phi factor for LRFD of 0.9 to get an available strength of 440 kips, which is quite a bit less than the required strength of 550 kips. So the existing column is not adequate, and we're going to need to design reinforcing. So in order to design reinforcing, we're going to use a symmetrical welded plate design as a first estimate of the area of the reinforcing plates. We saw in the previous page that the existing column was overloaded by about 25%, so we're going to try and increase the cross-sectional area of the column by at least 25%. So if we provide two 3/8 inch by 8 inch wide reinforcing plates, that'll increase the area from 19.4 inches to 25.4. we'll need to check the slenderness ratio to see if it meets the requirement of Chapter B. If we do that, we see that it does. If we didn't meet that criteria, you may want to consider increasing the thickness so you don't have slender plates as part of your column. And then in order to evaluate the strength of the reinforced column, we just need to calculate the section properties. So again, the moment of inertia and the radius of gyration of the reinforced section, which is just equal to the square root of I over A. And we get a value of 2.52, which is approximately equal to 2.58, which was the radius of gyration of the unreinforced section. So we meet the stabilizing criteria. So now we just need to go through the same equations that we looked at before, looking at and substituting in the section properties of the reinforced section. In this case, we have the original steel was 33 KSI, the plates are 36 KSI, so conservatively we're going to use 33 KSI for the full section. So the elastic buckling stress, using that same equation but subbing in the new radius of gyration, gives us a value of 49.3 KSI. The critical buckling stress is 24.9 KSI, and the nominal compression strength is 632 kips. Applying the phi factor, we get a strength of 569 kips, which is greater than the required strength of 550 kips. So this reinforcing design is adequate, and we just need to design the welds just like we did for the beam. So the requirements for welding the plate come from specification section E6 for built-up columns is applicable here. So again, we designed the termination welds for the yield stress times the area, or 108 kips. If we consider a 1/4 inch fillet weld, the required weld length is then calculated directly as 9.69 inches, where this 5.57 kips per inch is the strength per inch of a 1/4 inch fillet weld. So we'll round that up to 10 inches for our termination welds. There are a couple prescriptive requirements from section E6. This one limits the ratio between A, which is the distance between the intermittent welds. The ratio between A over R has to be greater than 40. And if it's not, then you need to use a modified slenderness ratio. Since we're pretty close to the capacity, we'll design our intermittent welds to meet that slenderness ratio capacity, so we can solve directly and find that we need to have an A or a weld spacing of 4.32 inches. So we'll use intermittent welds 1.5 inches long at 4 inches on center. And then another prescriptive requirement is that the A over R ratio cannot exceed 3/4 the governing slenderness ratio of the built-up member. So if we take a look at that, we find that we meet that criteria, so the 4-inch spacing is adequate. And then lastly, we have this requirement from section E6.2, which says that the intermittent welds shall not exceed the plate thickness times 0.75 times the square root of E over Fy. So if we plug into that equation, we find again that the 4-inch intermittent weld spacing is adequate. So here's the final design. We have our 3/8 inch plates on both sides, 10-inch long termination welds, and then our intermittent welds 1.5 inches long at 4 inches on center. So this design is adequate, but in many situations it's going to be very difficult to install reinforcing plates like this. In most situations in buildings, you'll have beams or braces framing in at the floor levels, and you won't be able to install reinforcing plates over the full length of the column. So this can be dealt with in a couple different ways. One is to take a look at using different reinforcing configurations. For example, you could look at reinforcing using flange tip plates. These are typically offset a little bit so that you can weld them with fillet welds instead of groove welds. Another thing that you can do is look at reinforcing the column using plates only over a portion of the length. So if we take a look at that same column, we're going to take a look at seeing what the strength would be if we had the reinforcing plates installed only over a 8-foot length, or half of the 16-foot length of the column. So in order to determine the strength of this, we're going to refer to this paper by Dalal called Some Non-Conventional Cases of Column Design from 1969. So in this paper, the author tabulates the strengths of different columns with step geometries, which is equivalent to what we're looking at here with the reinforced section. So all we need to know to go into the tables is the ratio between the moment of inertia of the unreinforced section and the reinforced section, and then the ratio between the overall length and the reinforced length. They use the variable A for the reinforced length, which can be a little bit confusing. It's not an area, it's a length. So for this problem, our ratio A over L is equal to 0.5. The reinforced moment of inertia compared to the unreinforced gives us a ratio of 1.25. So going into those tables, we can get the value for the effective length over the original length. We'll interpolate between 1.2 and 1.3 to get a value of 1.02. So then we multiply our original length by that number to get an equivalent length of 16.3 feet. So basically what this is saying is that if we reinforce the column over only the middle half, then we have the same strength as a column that's 16.3 feet long, reinforced over the full length. So just quickly, you'll need to check two limit states. One is looking at your 16.3 foot long column using the same equations we looked at before instead of 16 feet. So if we do that, we get a strength of 563 kips, which is adequate. And then you'll also want to take a look at the unreinforced section of the column, 4 feet long. If we do that, so using the smaller section properties, but also the shorter unbraced length, we find that that's adequate as well. So basically, by reducing the length of our reinforcing plates, we've substantially reduced the amount of reinforcing and welding, and we've only reduced the strength of our reinforced column by about 1%. So again, here's the final design. Same plates, we'll use the same weld design that we use for the full-length plates. So a couple other ways that you can reinforce columns. One is to encase them in concrete. This would be designed using the provisions in Chapter I of the specification. This is pretty rarely done because you'll need to have access on all four sides of the column, and encasing it in concrete will, in order to get substantial strength and provide room for the confining rebars that you need, the size of the column will grow by quite a bit. So this 10 by 10 inch column would grow to 18 inches by 18 inches. Another option that's used sometimes is providing bracing. So if you have your direction of buckling, if you can provide some additional members to provide bracing at the mid-height of the column, that can be one way to strengthen the column. So the last thing I'll talk about here for the last just 5 minutes real quick is how to evaluate and design strengthening for existing connections. So we'll use the same design procedure that we use for beams and columns. Again, we'll use the provisions of the code, of the current code in Chapter J, and from Appendix 5, we can make some conservative assumptions if we don't know the strength of the existing bolts or rivets. So for rivets, we can assume ASTM A502 grade 1. If we look in historic steel specifications, which are available in Design Guide 11, we can find a tensile strength for those of 52 KSI, and then evaluate the rivets the same way you would evaluate a bolted connection without threaded parts. So let's take a look at quickly evaluating and designing strengthening for this example connection here. We have a beam with double angles and 5 rivets through the web of the beam and 10 rivets to the column. So we need to evaluate all the different limit states, but the one we'll check first is rivet shear. So again, we have our tensile strength from the historic specification, and then the nominal shear strength from table J3.2 is 0.563 times that tensile strength, so we get a value of 29.3 KSI. And then the strength of the 5 rivets in double shear, or the strength of the 10 rivets to the column in single shear, is just equal to the shear strength times the area of the bolt or rivet times the number of rivets in double shear. We get a value of 130 kips. And then apply a phi factor of 0.75, and we can see that this existing connection is pretty substantially overstressed. I won't go through it, but we'll also need to check these other limit states for the connection to see if they control. In this case, they won't. It's the rivet shear that's controlling the design. So a couple different options for how you could strengthen this connection. One would be to replace the rivets with higher strength bolts. So for example, we could take out our rivets and replace them with 3/4 inch diameter A325 bolts. We can look up the strength of that directly in the tables in table 7-1 in the manual and find that retrofit would give us the required strength. So in order to do that, you chisel off the rivet head, push it out, but you have to be very careful not to damage the angle or the bolt or the rivet hole. So it's usually a good idea to provide shoring when you're doing this kind of work, because there can be some deformation of the connection. If you have enough strength, with say if we have a 5 rivet connection here, if 4 of the rivets are adequate for the loads at the time of strengthening, you could eliminate the shoring and potentially specify that the rivets be replaced one by one. And if replacing with A325 bolts isn't adequate, you could look at using higher strength bolts, A490 bolts, or larger diameter bolts, where you'd need to increase the size of the existing bolt holes. Another option is to replace only some of the rivets. If you had a connection that didn't need to be strengthened by quite as much, you could replace only some of the rivets with slip critical bolts. Section J1.10 in the specification allows you to share loads between existing rivets and new bolts that are tightened to slip critical criteria. Another option for strengthening existing connections is to add welds. So this is addressed specifically in section J1.9, where it says that if you have an existing riveted connection, you're allowed to design the welds that are using to reinforce that connection only for the added strength or the required additional strength. And the welds have to be able to provide the additional required strength, but not less than 25% of the required strength. So typically when we're designing new connections, we're not combining welds and bolts because of the lack of stiffness compatibility, the welds being much stiffer than the existing than bolts. But in this case, if you have an existing riveted connection, the existing rivets will take the load present before the reinforcing, and then you can assume that the welds, since they're much stiffer, are going to take the loads that are added after the welds are installed. So I won't go through in detail how to design this, but for this same connection design, you could come up with this welded reinforcing design where you're welding the angles to the web of the beam and to the flange of the existing column. And then one last method for strengthening is to try and add a seat below the existing beam, as shown here. So in general, you don't want to add a unstiffened seat because it doesn't have good stiffness compatibility. This is going to have to deform quite a bit before it can take any load from the existing connection. So if you're going to use a seat to reinforce the existing connection, you should consider using a stiffened seat, a welded stiffened seat. So that can be done directly using the tables in the manual. So from specification section J1.9, you could design the seats for a welded seat only for the loads not present at the time of the seat installation. Because there's some uncertainty about the deformation compatibility, in this example we'll conservatively consider the full load of 165 kips. So for this example, we have, if we consider a seat width of 4 inches and a 5/16 inch weld, we'll need a seat length of 14 inches in order to get the required strength out of the reinforced connection. So what the reinforced connection would look like is this. So the detailing for this comes from manual figure 10-10B. One thing that's where you get the geometry for this angled seat. One thing to notice is that the connection between the seat and the bolts needs to be bolted, and this is to provide the needed ductility in that connection so that the connection can handle the deformations that it's going to see when the load is transferred to the seat. So that's it for my presentation. I'll hand it back over now to Nate, who will field some questions from the audience.
All right, thank you very much, Joe. We do have a few questions from the audience we'll try to get to, but first we have a couple of participation polling questions we want to pose to the audience. And so the first polling question is this. A chemical composition test is typically used to determine which of the following. Is it A, weldability, B, yield stress, C, year of construction, or D, base metal notch toughness? And we will just pause here for a moment to let everybody submit their answers. All right, Joe. It seems like the answer A was the overwhelming favorite. Is the audience correct?
That's correct. I guess that question was too easy.
All right. Well, let's see how they do with the second question here. Second question goes like this. When reinforcing an existing riveted connection with welds, the welds are typically designed for, is that A, the full required strength of the connection, RU final? Is it B, half of the required strength of the connection? Is it C, RU prime, the loads present at the time of alteration? Or is it D, the required strength of the connection minus the loads present at the time of alteration, but not less than 25% of the required strength of the connection? We'll give the audience just a little bit more time to get their answers submitted. We're going to close the poll. And for this one, Joe, it looks like the audience thinks it's D.
Yep, that's correct. That comes from specification section J1.9. I would say also that if you answered A, that's not incorrect. It's just conservative, but the spec allows you to design the welds only for the loads applied after the welds are installed, but not less than 25% of the required strength.
All right, Joe. We'll do just a few question and answers from the audience here. The first question is on slide 22. Can you explain the required applied load magnitude for evaluation by load test? If we're determining the actual strength of the member, why wouldn't you use AISD level load?
Yeah, so if you're doing a load test, you want to make sure that you have your factor of safety. So the code requires you to apply the factored loads to make sure that the strength is adequate for those loads, so that in the unlikely event that the structure is loaded to that level, you don't have an unsafe condition.
Okay, thank you. Next question comes on slide 39. And the question is this: is it a requirement to use the current AISC specs to evaluate the strength of a member, or do we have the choice to use the 1965 code in this instance?
So, I mean, I would say that it's not necessarily wrong to use the old code. You're probably going to get a similar or more conservative result. But if you do look at Appendix 5, the language in there I think is pretty clear that the available strength of members, this is for evaluation existing structures, shall be determined from the applicable provisions of this specification. So again, I would say you're probably going to get very similar or more conservative results using the older code, but the Appendix 5 directs you to use the current specification.
The next question is on slide 50. A deflection of 0.448 inches was shown. Was this determined using a non-prismatic nature of the reinforcing member? Can you elaborate a little bit on how this was determined?
Yes, it was determined using that. So it's a difficult calculation to do by hand. Typically, you want to put this into a structural analysis program such as RISA or SAP. You would model a section of your beam with the lower moment of inertia, the middle section of the beam with the higher moment of inertia, and then the end section again with the lower moment of inertia, and then apply your loads and determine the deflection that way.
Okay. Our next question is on slide 60. In this slide, the bent plates and angles bolted to the new vertical plate top plate, are they acting as additional compression area in this case?
They are. So I didn't go into it in detail, but originally our detail was to have a WT shape in order to get that additional area at the top of the section. But the contractor was having difficulty getting access to the welds down here, so we came up with a design where first this middle plate was installed for the reinforcing, and then these additional plates, both the shelf plates for the new slab and these additional angles for the reinforcing, were bolted after this plate was installed. And then these bolts were designed for the shear flow so that these angles are contributing to the strength of the reinforced member.
All right, thank you, Joe. That's the last question that we have time for today. I do have a couple of closing remarks that I'd like to leave you all with. First of all, I want to mention again that the design guide that Joe talked about today, the second edition of Design Guide 15, will be soon available. And that's available both in print version for purchase, but also you can visit our website at aisd.org/publications, and you'll find that you can also download it as a PDF. And that PDF is a free download for AISC members. I also want to talk about, again, about retrieving your PDH certificates. You'll receive an email from registration at aisd.org within 2 business days. So be on the lookout for that email. There will be an online form that you have to fill out for you and all people at your connection. And filling that out with the AISC website username and password will enable you to then get emails sent out to each of those participants at your connection with their certificate for PDHs. I also want to highlight for you some upcoming live events that AISC Continuing Education is putting on. Currently, we are traveling around and doing a half-day seminar on the 15th edition of the Steel Construction Manual. This is being presented in 13 cities in the spring of 2018. Most of those cities are remaining. Cities include Philadelphia, which actually has a seminar next week, Houston, Los Angeles, and many more. So definitely go to our website, AISD.org/seminars, and check it out. And a key feature of the seminar is that participants will be eligible to buy the manual for a very reduced purchase of only $125. And before we part, I just want to thank everybody. I want to thank Joe for presenting to us today. And thank you all for your participation. There will be a survey that pops up on your computer screen at the close of this presentation. Please take a moment. It's a very short survey, but for us it's very helpful so that we can continue to improve and cater these types of events to what you are looking for. So with that, I will close the webinar today. Thank you very much. And